This time, let us consider a very beautiful problem, which is Article 7 of our textbook. On sides AB, AC produce the necessary of triangle ABC, we are to construct 2 points, points D and E, such that segments AD, DE, and EC shall be equal to each other. It is indeed a construction problem, but we could extend it to some other aspects of geometry. So, here we have triangle ABC. So, our task is actually to locate this point D and point E. So, we can assume that this is indeed the solution, okay? So, but if you notice, I can make use of point B in this case. So, what will I need to do? Well, I can first construct circle B with radius equal to AB and let the intersection be K. Okay, so what is that? Let me show that particular step here. That's step 1. So you notice I constructed circle B and the radius is AB, hence I will produce isosceles triangle ABK. That's the one. Okay? Next, I can construct another triangle this time, but this time I will make use of center K. Radius is either AB or BK. So radius is equal to AB. And let L1 be the L1 and L2 be the intersection with line LC. That is step 1. That is step 2. Now, step 2 is point K. Construct it with radius equal to AB. Hence, it will intersect this line here. We at point L2 and point L1. So, let us set aside point L2 first and let's just focus on L1, okay? So you notice, people, that this pink triangle here, BKL1, is another isosceles triangle because I constructed the circle K. But the yellow triangle is also isosceles with B as the vertex angle. The pink triangle rather, is an isosceles triangle with K as the vertex angle. Wow, wait a minute. BK is equal to KL1 is equal to AB. That seems to be okay. But the problem is B is not the same thing as D. But definitely it satisfies the fact that it has to be on this portion of the triangle and this portion of the triangle. Okay? So, well, I can do a backward method. And once I located L1 rather, I can construct BL1 and then construct from point C, construct a line that is parallel to BL1 to locate point D. Okay, so that is step 3. That is step 3, construct CD that's parallel to BL1. Wait a minute. I am going to do backwards one more time and make use of BK. And I want to construct DE parallel to BK. That's DE parallel to BK. By that construction, I was able to locate point D inside the triangle and point E inside the triangle. So those are the 2 required points. And you notice that we have many similar triangles here, okay? The blue triangle is this one, okay? So that's the blue triangle is similar to the yellow triangle. Keep in mind that the yellow triangle is isosceles triangle, and therefore the blue triangle is also an isosceles triangle that makes AD equal to DE. That's exactly what we want, AD to be equal to DE. Furthermore, the brown triangle DEC is similar to KBL1. And KBL sub 1 is another isosceles triangle with K as the vertex angle that makes this triangle also isosceles with DE equal to EC. And hence, we are done with the situation, because what we did was to construct triangle ADE with AD congruent to DE, and we constructed the pink triangle with DE congruent to EC, and hence that is the solution. Okay? Let us hide that. Let us hide this, and let us hide this one too. And that's what it is. Let us check the actual value of AD. It's equal to 4.13. DE is equal to 4.13, and EC is equal to 4.13 centimeters. If I drag it, it's always the same thing. But there is a possibility that B and D will coincide to each other, and that's what it is, okay? But that's varies, okay? The key idea here is the fact that I need to construct similar triangles, this parallel to this, and this line parallel to the other line, okay? That's how easy it is. So, very simple problem, but this time, you must remember, people, that I have another point K here because KL1 is equal to KL2. So let's consider that possibility here. So here's the thing that we've got here. So that's a blue triangle. The first solution is that one. Okay. AD1 is equal to E1, D1E1 and E1EC. That's what this one is. It's about 4.47. But keep in mind that there is a second solution. And that is, instead of considering E1, I need to consider a little bit away from the triangle, and that's E2C2. And then this one lies on line AC. And then on the other side of it is D2, which lies on line AB. So from point A, I have point D, and its distance from A is 11.83. D2, E2 is also 11.83. And finally, E to C is also equal to 11.83. The procedure here is nothing but this same procedure. It's just that instead of using L1 here, I will use it on this other side, okay? And that's what you've got. So here's the procedure. So K will always have a unique solution. There are two unique positions for L, leading to two distinct pairs of solution, D1, E1, and also D2, E2. If BAC is 90 degrees, K lies on A, and there are still two solutions. If angle BAC is equal to 60 degrees, one of the L's lies on point A, meaning that the line drawn in step 3 never intersects AB. In this case, there is only one solution. Now, guys, let us try to extend this problem from another perspective. We kept on doing construction. Why don't we convert it numerically? So I just thought of an 8, 11, 14 triangle. And there are several ways to look at it, but I wanted my A, which is this side, to be equal to 8 units. B is opposite B, so that's line segment AC, and that's 11 units. And C is the longest one, which is AB, is equal to 14 units. So you notice that in my solution here, D is inside the triangle and E is inside the triangle. So this is just one of those two solutions that we've got in here. Okay, so what is it that we can do here? Okay, so what I did was, so the triangle I constructed is similar to an 8-14 triangle because the basis here is I constructed segment PQ, I increased PQ by 14, I increased PQ by 11, and I increased PQ by 8. Therefore, I am able to construct a triangle similar to 8, 11, 14 triangle. And that's what it is. Okay? And hence we have all these things. So, let's do now the numerical computation now. Okay, away from the construction problem. So ADE, this triangle, I reconstructed it on this side, is an isosceles triangle, and therefore, because AD is congruent to DE, and therefore I can construct point Q, which is the altitude here, and hence cosine A is equal to AQ divided by the hypotenuse AD. Or if I double it so that I can have AQ, double it and double the denominator, so we have 2AQ over 2x is equal to AE over 2x. But AE is actually the length of B minus x. Okay, it's this one is equal to x. So in that case, and that's 2x. And wait a minute, we do know what cosine law is. Okay, cosine law for angle A gives you the formula b squared plus c squared minus a squared all over 2bc. And compare this with the other cosine A. Therefore, I have this b minus x all over 2x. Okay, and therefore, just separate this one, 2 over bx minus x over 2x is equal to minus 1/2. And with that, we have the following simplified version, and algebra leads us to x being equal to b squared over c, b squared times c all over b squared plus c squared minus a squared plus bc. But this is the assumption. The assumption here is the fact that a point D is inside the triangle, and hence this will be equal to C minus X, and this is equal to B minus X. And with that, I just replace A, B, and C in my formula. I end up with 134 over 37, or B is equal to 4.16, which confirms with our computation here that the whole value of AD, which is equal to X, is equal to, let me change this one to X, and X is equal to 4.16, which is here, okay? Solving it differently this time, we still have A is equal to 8, B is equal to 11, and C is equal to 14. So, a while ago, we solved points D and E inside the triangle. This time, maybe we can find points D and E where D is outside the triangle and it is on line AB, and point E where E is on line AC. So points D and E are both outside the triangle. And how are we going to do this? So here's the thing that we can do, okay? So AB is equal to 14, BC is equal to 8, and AC is equal to 11, okay? But I also know that BK by construction is an isosceles triangle, so by construction, BK is also congruent to AB, so AB is 14, BK must also be 14, okay? So, with this triangle, I know that I can solve for CK using the Stewart's theorem. Okay, How are we going to do that? Okay, let us recall what Stewart's theorem is. It seems that I'm a little bit rusty, so let's recall what the Stewart's theorem is all about, okay? So the Stewart's theorem, in almost all textbooks, there is a mnemonic device that we can use. It says, a man and his dad put a bomb in the sink. This just helps us remember that MAN plus DAN is equal to BMB plus CNC. Man plus dad equals bomb plus sink. Or we can algebraically simplify this by factoring A on the left-hand side. A times Mn plus D squared is equal to B squared times M plus C squared times N. What that means is this. We have the orange triangle, and in this orange triangle, we have Chavian. AD is called Chavian, after the Italian mathematician who discovered properties about it. Chavian AD is, D is on segment BC, and the segment that connects point A and D is the Chavian. So we are trying to relate segment C, segment D, segment B, segment M, segment N, and segment A. Okay, so that's what we've got here, and we'll see that. Let's verify that one. A in this case is 25.09, B is 17.08, C is 14.3. The Chavian is 9.49, and then this segment A is divided into segment M and segment N, where M is 12.32 and N is 12.77. I find the product of MAN. M times A times N plus DAD. D times A times D is equal to 6206. Whereas bombed plus sink is equal to 6206. It seems to be that they are always valid, equal to each other, okay? Let's verify that. Let's move it further. The product's still the same. Move it again. The product is always the same, okay? Okay, let's try to prove this using simple algebra. And let's say put it here, okay? So if I put that there, I can construct altitude AH here. And with that, I now have here D squared is equal to H squared plus B squared. D is equal to H squared plus B squared. Everything is Pythagorean theorem, okay? And then second one, I will make use of this triangle, okay? So that is now equal to B squared is equal to H squared plus this whole segment, which is N plus P squared. Simplify this to D squared minus P squared plus N squared plus 2NP plus P squared. Cancel the P squared and the P squared. We end up with the following expression. Similarly, I will use this particular triangle, but making use of this triangle again. So C squared is equal to BH squared plus H squared. But there is another expression for BH. BH is the same thing as BD minus P. And that's what it is. And I can replace BD by M. Okay? So, because keep in mind that when Chavian is not there, okay, the altitude is not there. Okay, Chavian, sorry. This BD is the one that is equal to M, okay? BD is equal to M. So let's put it back. That's what it is. So BD minus P is the same thing as M minus P. Expand this, it becomes M squared minus 2MP plus P squared. We can cancel P squared and P squared here. We end up with D squared plus M squared minus 2MP. Wait a minute. I want to create bomb, BMB, and I want to create sink, CNC. And that's why I need to multiply this first expression by M and the second expression by N. If I multiply it, it becomes like this. And if I multiply c squared by n, it becomes sinc, and then the other one is bomb. Okay? So if I add the top with the bottom, I end up with b squared m plus c squared n is equal to these two. I can factor out the d squared, and it's m plus n. These two, I can factor out m times n, and common factor is m plus n. And these two cancels out, it becomes 0. However, we know that m plus n is equal to the whole length a. So, m plus n is equal to a. Therefore, the bomb and the sink added together is equal to the dad and the man. Hence, with the Stewart's theorem, we are ready to solve this problem, okay? Triangle ABK, okay? And with triangle ABK, here it is, ABK, BK is the same thing as AK, it's equal to 14, okay? By construction, AB, BK, and KL are all equal to 14, which is the longest side of the triangle with sides 8, 11, 14. And therefore, AC is equal to 11, okay? And therefore, I can subtract the rest, okay? So, by the Stewart's theorem, we have the bomb, the sink, the dad, and the man. 14 squared times AC is equal to 14 squared times CK is equal to 8 squared times AK plus the M, N, and A, AC times CK times AK, and then I can factor out the 14 squared in here. That's why it becomes, okay, AC plus CK. AC plus CK is the same thing as AK. That's why I made it as AK. And then this, I put them together, and that becomes a 64 plus AC plus times CK times AK. So both of them have AK. Just cancel the AK. We have now 196 is equal to 64 plus 11K. Simple algebra will lead us to CK equals 12. So CK is equal to 12, and therefore AC is equal to, AL is equal, KL is equal to 14, as we know, because BK is equal to CL is equal to 12, and there 14 rather, and therefore since this is 12, the leftover will be 14 minus 12, and that's equal to 11, equal to 2 rather. But wait a minute, I do know that AC is equal to 11. That's the side of the triangle ABC, and therefore the leftover AL is equal to 9. Now, with these results, I now have all of this, 14, 9. Hence, I now have here similar triangles. Okay, this is now ABL is similar to ADC, and therefore AD can be divided by AB, and that's the same thing as AC divided by AL, and the rest is just replacing it. Simple algebra will lead us to AD is equal to 154 over 9, or 17.11. So this is the case where points D and E are outside the triangle. In the previous problem, points D and E are inside the triangle. Well, let's solve another one. And that is the 5, 12, 13 triangle. And I think everything is easy, but I guess we just, the takeaway here is that we need to adjust our construction, because in this case, cosine A here, again from the right triangle, is equal to 12 divided by 13. But from triangle ADE, okay, AE is equal to 12 minus X. And if M is the midpoint of AE somewhere here, okay, then AM is equal to 12 minus x over 2. And hence, let me show you where M is. There is M. And construct D and M. There you go, people. So AM is equal to 12 minus x divided by 2. And therefore, cosine of x, cosine of angle A rather, using this triangle, ADM, is 12 minus x divided by 2 divided by the hypotenuse x. And replacing this with 12 over 13, we have the final value of x, which is 156 over 37. Wow, it's very interesting. I can change it in such a way that my triangle is, let's solve first this one. Okay, this is also 5, 12, 13, but this time the solution will be outside. Okay, AD, D is outside, DE is also equal to AD, E is again outside, and EC are all equal to each other, and that's equal to 15.36. Okay, how do we solve this? Okay, I think it's so easy now. We do not need to we will not have any difficulty here. So, again, we know that ADE is isosceles, okay, with AD equal to DE, okay? Therefore, cosine of angle A is equal to AQ divided by AD. If I double it so that I can have AE, double AQ, it becomes AE. If I double it, I need to double it also. That's why it becomes AE over 2x. But AE is actually equal to 13 plus x. Okay, AE is 13 plus x, and therefore I have this value, and the other value of cosine A is 12 over 13. Putting them together, simple algebra will lead us to 169 over 11. So that's what it is. Finally, I just reverse it. Just another interesting situation is the fact that in this 5, 12, 13, the hypotenuse is segment AB. Whereas in this situation, AB is the leg of the triangle with sides 5, 12, 13. And therefore, AB this time is 12. And AC is the hypotenuse with length equal to 13. So I need to do, I just need to twist certain values, certain computations. And in that case, I will have this one is x, this one is x, and this one is equal to x. And therefore, cosine x is again 13 minus x over 2 divided by x. But cosine A this time is 12 over 13. And putting them together, x is 169 over 37, which is 4.57. Wow, that's kind of awesome. It's very difficult. The problem is originally a construction problem, but from the construction, we can raise so many questions numerically, and it will involve another aspect of mathematics. See you again in the next discussion of another article. Thank you very much. Bye-bye.